Okay, it's time to move on and now start to think about the chemical shift, the position our peaks have in our NMR spectra. Now, chemical shift is the fancy phrase that we NMR spectroscopists use to talk about peaks that are on the right side of the spectrum, the left side of the spectrum, somewhere in the middle of the spectrum. So it's essentially the position of the peaks. And the same phrase applies to whether we're talking about proton or carbon, fluorine, phosphorus, or any other type of NMR spectroscopy. And we concern ourselves with chemical shift quite a bit because it can be very diagnostic. There are certain functional groups that will show up only in certain areas, and so if you do see a peak, say at around 10 ppm, you are quite certain you have an aldehyde. If you don't see a peak there at 10 ppm, you can be pretty certain you don't have an aldehyde as a part of your sample. So this is very useful to be able to recognize some of these basic areas, and it's yet another part of our learning to how to interpret NMR spectra. Now, some terminology. The technical words that the NMR spectroscopists use to talk about this stuff are technically upfield and downfield. Upfield stands for the right side of the NMR spectrum. Downfield is the left side of an NMR spectrum. The terms come from the good old days at NMR when it was literally a magnetic field that was being changed, moved up or down, and that is how you recorded a spectrum. It's not done that way anymore, but the phrase upfield, downfield are still with us. So if you look at a spectrum like this one, this is our dear friend methyl ethyl ketone. We've seen it before. A student at a somewhat lesser university than Georgia Southern would say something like the methyl group at position A is to the right of the methyl group at position D. A Georgia Southern student, on the other hand, impressing others with their NMR knowledge, would say something like the methyl group at position A is upfield of the methyl group at position D. There are plenty of resources available for looking up chemical shifts. There are some that I've put on the course website. Frankly, if you just Google proton chemical shifts, you'll end up with more things to look at than you can possibly do in one lifetime. There are a lot of resources out there. I tend to like a graphic that looks something like this. It tends to be, I think, easier for me to interpret rather than just simply a table of numbers. And so I'm going to use this one. And while there are, of course, dozens and dozens of functional groups to look at, there are some that I think it's important for all students to have a basic idea of where they show up in an NMR spectrum. And we're going to look at proton chemical shifts first. And so this graphic kind of tries to summarize some of the basic ones, and I want to walk you through some of the most important chemical shift regions to look at. So starting on the downfield side, on the left side of an NMR spectrum, is the region around 10 ppm. This is a fairly uncrowded region. There's not a lot that shows up down here. Aldehydes are by far the most common functional group that appears here. And so if you do see a peak here, you almost certainly have an aldehyde. This is one that's very diagnostic. There's the area around 7 to 8.5 to 9 ppm. This is the aromatic region in a proton spectrum. There can be other things here, but by far the most common functional group is a benzene ring. And in fact, if you could integrate the thing, you could often tell if your aromatic ring has one substituent on it, and therefore 5 protons, or if it has 2 substituents on it, therefore it'll have 4 protons. And so that can be a very useful region to look at. Another one is the area of roughly 5 to 7 ppm, and it can vary a little bit. There is some overlap. This is the area of the alkenes most often, protons on carbons that are a part of a double bond. Like I say, aromatic regions and alkene regions, they can overlap. There are some alkene peaks that creep up into the over 7. There are some aromatic peaks that can creep down below 7. But these are general rules of thumb to use. The area around 4 ppm is another really important one. These are hydrogens near highly electronegative atoms, the most common one, of course, being oxygen. And so hydrogens that are near the OH of an alcohol, or near the oxygen of an ester, or near the oxygen of an ether tend to show up in around 3.5 to 4.5, right around the zone of 4 ppm. Another very useful area. The most upfilled one that we can make use of quite often is the area around 1 ppm. These tend to be methyl groups, especially methyl groups at the end of a long chain of carbons. If it's far away from anything that's electronegative, they can be around 1. They can even be slightly less than 1 at 0.9 or 0.8 ppm. And in fact, generally, there are plenty of exceptions, of course, but generally your most upfield peaks tend to be methyl groups. Okay, it's not uncommon for that to happen. Now, the area around, let's say, 1.5 to 3.5 ppm, there's a lot of stuff that shows up in this area. CH2 groups in linear molecules and in cyclic molecules and groups near carbonyls and so forth. So this is probably one of the most crowded and complex regions of a proton NMR spectra. It can be quite useful for integrating and other things, but as far as saying, oh look, there's a peak at 2, it must be dysfunctional group. That's kind of a difficult one to be able to do here.